solve the practice problems. Okay, so I'm going to get started now. So PowerPoint. Okay, so someone's asked me number 3 of 2D dynamics, 2D kinematics. So number 3 of that, relative to each other, you just have to use the Pythagorean theorem. One car is at 35 kilometers an hour, the other one is at 55. So you just square those two and take the square root. And for the number 4, setup, you just turn the velocity into x and y components, and then you would just find the amount of time based on how the y component, and then find the x component from there. So yeah, and the number 1 for basic is if the elevator is accelerating downward at 2 meters a second squared, then that means the force of gravity on the person, like to the scale, it seems like you're lighter, right? And you would just do 9.8 minus 2, and so that's the apparent force of gravity on you, and then you would divide that by the actual reality, which is 9.8, and multiply that by 60. So that would basically be 7.8 times 60 over 9.8. All right, so it seems like more people have come.
Tablet 就是我的那个 iPad Pro.
Okay, I'm going to share my screen now for today's class. So today we have circular motion. We're going to be talking about everything that goes in circles. Okay, so this may include, so we're going to talk about balls on strings. We're going to talk about cars going in circles and all that stuff. Okay, so the topics we're going to discuss today are, first one is centripetal force. Then we're going to talk about period and frequency. And then we're going to go to some common applications of circular motion. So first of all, centripetal force. Well, let's first start with Newton's first law, the first law. What's the first law? Well, we kind of neglected it in dynamics, and we're going to look at it again here. So the first law states that the velocity of an object cannot change unless a force applies to it, right? So if there's no force applying to an object, its velocity will stay constant. And remember, velocity is magnitude and direction. Okay, so if there's no force acting on an object, neither the magnitude nor the direction of the velocity will change. So all objects tend to go straight on their path, right? If there's no force acting on an object, its magnitude is not going to change, and its direction is not going to change. All right, but if we have an object moving in a circle, it may be going at some velocity at this instant, and then its direction has changed. So that means some kind of force has actually acted on it, even though the magnitudes of velocity haven't changed. So if the direction of velocity changes, then some kind of force was applied to it. So this is what we call centripetal force. Centripetal force is the force that makes an object go in a circle. Okay? And also an important thing to note here is that when an object is going in a circle, velocity is always tangent to the circle. As you can see here, as I drawn, its velocity vector will always be tangent to the circle. Okay? So what is that force that's causing the velocity to go around in the circle? Well, there is a formula for the acceleration, and this is quite a crucial formula here. It's v squared over r. Since I have a lot to cover today, I'm not going to go through the proof for this formula, but this is the acceleration that requires an object to change velocity for a certain velocity v and the radius r that the circle has. So this is the formula for the acceleration. So therefore, the force equals ma, or mv squared over r. Okay, and this formula actually makes sense. Okay, right? Because if you were to drive around a circle and you were to drive around at higher speed, then you would feel a greater force pushing you in that circle, right? So that's how we know force is directly related to the velocity. And then if you were to go around a small curve at some speed rather than a big curve, then the force would also be higher. So that's how we know force is inversely related to the radius. So what direction is this force being applied in? This force is actually always being applied perpendicular to the velocity vector. Perpendicular. Since the velocity vector is a tangent, that means the force is always directed along a radius of the circle. All right, and so is the acceleration. Okay, so for an object to go around in a circle, the force applied to it is actually going perpendicular to its velocity, and that's going to make it go in a circle. Okay, so these two formulas for the acceleration that's required for some kind of velocity and some kind of radius, these are actually really crucial, and I think you guys should memorize this to understand how to do these problems. Okay, so maybe write those down in a notebook. So these are really important stuff. A common misconception a lot of people have about this one is I was confused about this too. Like if I have some kind of object going at velocity, right? I have a box going this way. If I apply a force perpendicular to it, it's just going to push it in some kind of diagonal path, right? That's how it works, right? So this kind of like makes it seem like, hey, this object's not going to go in a circle. If a perpendicular force is applied to it, it's just going to go on a diagonal path. So the key here is that the force on this object is always being applied downward. Okay? But as you can see on the circle, as the velocity vector changes, the force vector is also changing. See how the force vector has changed direction as well? So if the force vector follows the velocity vector, such that the force is always perpendicular to the velocity, then the object will go in a circular path. If the force is always directed downward like this, then it's going to go in a diagonal path. Okay? So are there any questions about that? All right, let's do some problems with these. So again, the critical formula that you need to know is the acceleration that's required for this object to go in a circle for a given v in an r, that's v squared over r. So the force is therefore mass times acceleration, or mv squared over r. If you get the answer, maybe you can chat this one to me, chat the answer, and then if you want to explain this solution to the class, then please say so. So some people have given the answer to number 1 already. So if you solved it and you want to explain this, please say so to me in the chat. I already have someone signed up for number 1. So if anyone still wants to explain number 2 or number 3, please chat that to me. Okay, so I think most of you are done already. So for number one, I'm gonna have Fiona explain this one. So if you would turn on your mic, and I think you can annotate on my screen. Yeah.
Okay. So you just use the formula A is equal to V squared over R, this one, and you substitute 3 for R, and you have a velocity of 4 m over s. So 4 squared is 16. And when you put that in the calculator, that is roughly 5.33 or 5 1/3.
Yep, that's exactly how you do it. So for the next one, we're gonna have Tyler share the answer for this one. So if you would unmute, and I think you can annotate on my screen as well.
For number 2.
I think you're muted.
Yeah. Hold on. Okay. So for number 2, you use the F equals mv squared over r equation. And since you want to find the radius, you solve for r, and that's r equals mv squared divided by f, and then you just divide. You just input the values.
Yeah, so you just take the equation 15 equals 5 times v squared over r. And what is v? 10 meters a second? That's going to be 100 over r. So then that's just, wait a second. Yep, so then it's just 500 over 15, which is 33.33 meters. So for the last one, we're going to have Otto share the answer.
So we start off with the I started off with the formula. The force is m times v squared by the radius. So the force, which is the force, which is 27, is equivalent to mass times 49 by 2.
Yep.
And then if you simplify it even more, it would be 49 by 2, which is basically 24.5. And then so the mass is basically 27 by 24.5, which is basically 54 by 49.
Yep, and if you were to use that in the calculator, that would be 1.1. Okay, nice job, you guys. I'm going to skip this one for now because we're running low on time. So now we have period and frequency. What are period and frequency? These are common words you would use to describe an object going in circles. Okay, so first of all, what is period? Period is the amount of time it takes for the object to go around one revolution, go around the circle one time. So what is that time? Well, as we know, v equals distance over time. So what's the distance an object goes in one revolution? That's just the circumference of the circle, right? 2 pi r. Make that a little better. 2 pi r over t equals v. So then if you were to rearrange, t equals 2 pi r over v. So this is the period of an object's rotation. So if someone were to give you a period of 2 seconds, that would be the amount of time it takes for an object to go around the circle one time. Okay, so since this is a unit of time, we're going to use seconds. This is the unit we're going to use for period. Okay, so what is frequency? Frequency is the reciprocal of period. It's the it's how many revolutions in 1 second. As you can see here, these two are flipped. So frequency is just, we're going to label that as f, 1 over the period, which is t. Okay? So as long as you remember what period is, then you will know what frequency is. So frequency is the amount of revolutions the object goes around the circle in 1 second. Okay? And this is given in either revolutions per second, or another unit is hertz. Okay? So these two are the same exact unit. You can give your answer in either of these forms. All right, does anyone have questions about these? All right, let's do these. So if you guys would want to explain the answer to a problem you get right, then please say that, private that to me. I'm going to give you guys 1 more minute to work on these. All right, so for the first one, we're going to have Fiona explain the answer for that. So go ahead.
Okay, so you just use the formula T is equal to 2 pi r over V for the first one. And that would be T is equal to 2 times R, which is 20 times 3.14, which we use for pi, and all over velocity, which is 5. And when you do that, you get 20 times 3.14 is equal to 62.8 divided by 5 is equal to 12.56, and that is the answer.
All right, would you want to explain how you would get the frequency from that?
Yes, let me erase all of this first. The frequency as the frequency is just the inverse of the period. If you're doing this on in a rather advanced calculator, you can just do this as you can just press the button x to the power of -1, because frequency is just 1 over t. Or you could just do 1 divided by t. Either way, you would get 12.56. You would get 0.08.
Yep. And the units we'd use would be revolutions per second or hertz. So very well done. So now for the second one, I'll explain this one. So a ball's centripetal acceleration is 5 meters a second squared. If the radius of the radius of the circle is 7 meters, what's the period and the frequency? Well, acceleration is v squared over r again. And if we have r, which is 7, that's going to give us velocity. So v is just the square root of 35. 5.92. So the period is going to be 2 pi times r, which is 7, over 5.92, which is v. Let's do that. 2 times pi times 7 over 5.92. It's going to be 7.43 seconds. And the frequency is just the reciprocal of that, 1 over 7.43. Doing that, we're going to get 0.13 hertz. Okay? Now for the last one, if a period of a ball's motion is 2 seconds, and its velocity is 4 meters a second, what is its centripetal acceleration? Well, the formula for centripetal acceleration is v squared over r, and the period, t, equals 2 pi r over v. Okay? If we see here, we have r over v and v squared over r. So, if you were to plug values in here, 2 equals 2 pi times r over v, then that means r over v is just 1 over pi. So r over v is 1 over pi, right? If we were to take the reciprocal of this, then v over r is pi. And now to get from v over r to v squared over r, all we have to do is multiply this by v. So this is just 4 times pi. So 4 pi is equal to 12.57. Okay, are there any questions? So another approach to this problem is actually solving for r and then doing that. But if you're to look for these tricks here to manipulate the equations, then it gives you a rather quicker solution. Now we have the first common application of our centripetal motion. So we're going to talk about a ball on a string. So there are 2 types of situations we're going to encounter here. One is easier. We're going to consider a ball going in a horizontal circle. Okay, so if the ball goes in a horizontal circle, then that means some kind of centripetal force acts on it. So there's a string here, and therefore the tension in the string allows this ball to go around in a circle. So what does that mean? If the radius is r and it's going around at some kind of v, then that means the tension is just mv squared over r. Right, that's simple enough. So now what about vertical circles? If the ball were to go in a vertical circle. Well, at the bottom here, we know that tension is going to supply some centripetal acceleration, right? But then there's gravity pulling this guy down, mg. As we know, net F equals ma. So that means the sum of all forces equals mv squared over r. So that means we're going to have T minus mg as equal to mv squared over r at the bottom of the circle. Okay, does everyone understand how this works? Now at the top of the circle, tension is still going down, right? Because tension always goes towards the center of the circle. But now gravity is helping it. So in this case, T plus mg will equal to mv squared over r. So if the ball were to go at a constant velocity throughout this whole circle, then the tensions at the top and the bottom are going to be different. Okay? Because you have to consider the gravity that's going to be either helping or hindering the tension in making this ball spin. So that's basically the only extra thing you have to consider in vertical circles. All right, are there any questions about this? All right, let's do these. So these are all, both of these are horizontal circle questions. So in this problem, let's just set the velocity as 10 meters a second. So I think I forgot to put that in. For the second one, just to clarify, the radius is the horizontal component of, yeah, right there. Because if you were to look at the circle, then that would be the radius of the circle. So I'll give you guys 2 more minutes for these problems. So if you guys would want to explain the answer to a problem you solved, then please chat that to me. Okay, maybe 1 more minute. Okay, so I think for the first one, we're gonna have Autumn explain the solution. So you can go ahead.
Yeah. So for the first one, the tension is mass time. The tension is mass times velocity squared by radius. So the tension is basically 150 grams. By the 10 meter per second velocity. So we square that 100 by 0.6. And my calculator said that if you the whole thing is equal to 25,000, but since it's supposed to be this is in grams, we have to convert it into kilograms, so which gives you 25 because you're dividing by 1,000.
Yep. So instead of writing 150 here, you could write 0.15 kilograms. And that would give you 25. So nice job. Now for the second one, a ball is rotated around a circle as shown. If the ball moves around a circle of radius 0.5 meters with a velocity of 8 meters a second, what's the angle that the string makes with the horizontal? Let's first draw in a large version of this. So since the ball's moving in a circle, there's some kind of centripetal acceleration here, right? V squared over r. So why does the ball make an angle? Well, there's gravity pulling it down, mg. So let's write all of these in terms of accelerations, right? So you have g, an acceleration of g, and an acceleration of v squared over r. So what is v squared over r? That's just 8 squared over r, which is 0.5, 128. So centripetal acceleration is 128, and the gravity is 9.8. As you can see, we have a triangle of 9.8 and 128. So the angle theta is given by tangent theta equals 9.8 over 128. Okay? So theta equals negative tan, not negative tan, 10 negative of 9.8 over 128. What would that be? 4.4 degrees. Right here. Okay, are there any questions? So if you did the homework, there are a lot of problems. Like there was one about a plane and the plane taking off. So you would just have to consider these vectors and they will make a triangle. Okay? Now I've got two problems about vertical circles. So we're running a little low on time here. So maybe I'll give 2 more minutes for these problems. I know it's a little rush, but I want to make sure we can get through everything we need to get through. All right, I'm going to go ahead and explain these now. So for the first one, a 0.6 kilogram ball moves around in a vertical circle of radius 0.3 meters at a constant speed of 7 meters a second. What's the tension in the string at the top and the bottom of the arc? So let's first draw out this diagram here. Let's have the circle. That's a pretty nice circle there. And it's going at some kind of speed, I don't know, let me check, 7 meters a second. The radius is 0.3. The ball is 0.6 kilograms. So what's the tension in the string at the top of the arc and the bottom? So as I've drawn here, let's do the bottom first. So the tension in the string is applying centripetal acceleration, and gravity is working against it. So mv squared over r equals tension minus gravity. So if we move gravity to the other side, then mg plus mv squared over r equals tension. So if we were to plug the values in, that would be 0.6 times 9.8, adding to 0.6 times 49, divided by the radius, which is 0.3, 103.88 newtons. Okay, that's at the bottom. What about at the top? Tension is pulling it down. Gravity is helping it. So mv squared over r is tension plus mg. Now if we were to move, so mv squared over r equals tension plus mg. So moving mg to the other side, we'll have mv squared over r minus mg equals tension. So if we were to plug values in there, it would get, I think it's 92.12 newtons. Okay. So now for the next question. 1.5 kilogram ball is on the end of a 1.1 meter long massless cord, and it's swung in a vertical circle. What's the minimum speed required for the ball at the top of the circle for it to keep moving in a circle? So what is this question actually asking? As we know, if we were to swing a ball around in a circle, if we don't give enough speed at the top of the circle, the rope's going to fall limp. It's going to, as you know, the rope's going to go something like this. It's not going to be stretched out anymore. And if the ball were to be going in some kind of circular fashion, and then it would just drop some like in the path like that, right? So how do we know the ball is continuing to go in a vertical circle, in a circle? Well, as long as the rope remains stretched, then the ball will go around in the circle, right? If the rope is stretched, then that acts as a constant radius that makes a circle. Okay, so as long as the rope is stretched, the ball will be moving in a circle. So how do we know the rope is stretched? Here's something you should remember here. If a rope is stretched, then that means there's tension in it. If there's no more tension in the rope, then the rope is not stretched. So we have to look at the top of the circle where tension has just hit 0. That's the minimum value, right? If there's any tension in the rope, then the ball will keep going in a circle. So at tension equals 0, the only force supplying centripetal acceleration is gravity, right? So mg in this case equals mv squared over r, right? So at this point, this is the minimum value for velocity that we're solving. And at this minimum value, tension is equal to 0. If anything's above that, then the ball, for any value of velocity above that, then tension will not be 0, and the ball will go in a circular path. So now solving, we'll cancel the masses on both sides. So velocity is square root of g over r. Oops, let's kind of put that right there. Equals v. So what is that? 9.8 times 1.1. Square root of that. Velocity is 3.28. In just a second. Okay? As you can see here, the mass of the ball doesn't matter. All right, so now we've got second common application, cars. So as we know, sometimes roads are banked. What does that mean? Well, roads are like, they're kind of curved, they're inclined. That if a car were to drive like this, it would be easier. It would be easier for it to turn in some kind of circular path. And if you watch the race car games, you know that the track is really, really slanted for such a high speed. So why does banking help? Well, let's first look at a car on a level road, a flat road. Okay, this guy. So let's just assume he's on a circular track right now. He's right here, and he wants to go around in a circle. Okay, so there must be some kind of centripetal force pulling him towards the center of the circle. That's going to make him go around in a circle, right? If there's no centripetal force, the car's just going to go forward. It's going to go forward because in that case, Newton's first law says that the velocity's direction will not change. So what is that force being applied? If you look at the car in this view, then the only force supplying this could possibly be friction. That's the only force. And that's true. The friction here is actually static friction. Static friction is what supplies the friction needed for a car to go around a turn. So something important to remember here is that static friction is what gives the car the ability to go around a turn. So why is it static friction? Why not kinetic friction? The car's moving, right? Shouldn't that mean that the car is undergoing kinetic friction? But if we look at the instant right here, with the car just there, if we were to take a snapshot of it right now, it's going forward into the page, right? But is it going at any velocity left or right? Is it going at any velocity in this direction? Well, no, it's basically stable in that direction because it's not going anywhere. It's just there, right? It's only going forward and backwards. So since the object is not moving in the plane of static friction, in the plane of the friction, right? If there was any movement in this direction, then it would be kinetic. But since it's not, then that means the force is static friction. And another way we can see how this is static friction is if the car were to go around a long turn, right? If it were to go around a light turn, then the amount of friction needed, the amount of centripetal force needed will be less, right? If the car were to go around a steeper turn, then the friction needed will be more. So this kind of friction is actually changing, which means it's static friction. So static friction is what supplies a car's movement. So in this case, if we were at a flat level road, then the static friction, mg mu s, is equal to the centripetal acceleration. Okay. So what about a banked road? When the road is tilted, how does that help? Let's draw a diagram here. So what forces are acting on this car? Well, there's mg pulling it down, and there's the normal force perpendicular, right? So let's first look at these two forces. Normal force, as we can see, it's at an angle, right? We can divide this normal force into x and y components, right? Normal x, normal y. And as you can see here, the normal force is able to supply centripetal acceleration. If you're to draw the car on a track like this, it's right here. Normal force is able to supply centripetal acceleration if the car is on a bank, if the road is banked, okay? So what are these components of normal force? Well, let's do some geometry here. If we were to take the incline up here, this is theta as well. And so this is 90 minus theta, and this angle is theta. All right, so what does that mean? For a car on a normal, on a banked road, the angle theta is here. That means normal force y is n cosine theta. Normal force x is n sine theta. So n sine theta is what's supplying this car to go in a circle. Okay? So this is why if the road was not banked, then theta would be 0, right? And sine theta would be 0. So if the road is level, then normal force cannot supply any centripetal force because obviously it's perpendicular to the surface. All right? So this means that for a certain angle, if there's no friction on the incline, there might actually be enough normal force that exists to supply the needed centripetal force, right? So what is this case? Sometimes we don't actually need friction to go around a banked curve, right? Because normal force is sometimes enough to supply that. So in this case, n sine theta, in the terms of no friction, that equals mv squared over r, right? What is n cosine theta? Well, let's look at these forces in the vertical plane. mg exactly counteracts normal force, so mg equals normal force cosine theta. So n equals mg over cosine theta. If we were to plug in n right here, then mg sine theta over cosine theta equals mv squared over r. Cancel these. Since sine theta over cosine theta is tangent theta, then tangent theta equals v squared over r times g. So theta is the negative tan of v squared over gr. So for a certain angle theta and a velocity and a radius, if the angle theta satisfies this equation, then no friction is actually needed for the car to go around in a circle. So this is a formula you guys should remember here. This is the quote idealized curve, so that no friction is actually needed. The normal force is exactly enough to supply centripetal acceleration. But sometimes normal force is not enough, or normal force might actually be too much. So in this case, in the real world, friction will try to balance this out. Okay? What if normal force is too much? Sometimes normal force might be too much, such that the car is going to start slipping. It's going to start sliding down the plane. It's going to start sliding this way. So friction, if normal force is too much, friction has to counteract this. All right? So in this case, friction may go downward from the plane or upward from the plane. If normal force is too much, then friction will counteract it. It will go backwards. If normal force is not enough to provide centripetal force, then friction is going to go downward. Okay, and what are the components of friction? Well, let's first look at most cases, normal force is actually not enough. And in the real world, that's why we need friction. So if we look at friction here, theta, and so this case would be friction times cosine theta, and downward we would have f sine theta. So if you look at all the forces on this thing, we have n cosine theta up, n sine theta to the right, mg, f sine theta, and then f cosine theta. So there are a ton of forces you guys need to consider here. So in this case, both friction and normal force are going to supply centripetal acceleration, and you would find this using f cosine theta plus n sine theta equals mv squared over r. And then on the vertical plane, you can have the equation where n cosine theta will balance out mg and f sine theta. So you guys don't need to memorize this, but as long as you understand how the geometry breaks down so that these forces are going to go in certain directions, that's all you need to know. Okay, so in the real world, roads don't need to be banked as much because friction is going to help the normal force in supplying centripetal acceleration. Okay, so this is quite the advanced stuff. So common misconception a lot of people have is, hey, normal force in this equation is mg over cosine theta. From dynamics, we see normal force is mg cosine theta times cosine theta. What's up with that? Well, if you were to have an object on an incline, it's not moving in a circle, right? It's not moving around in a circle. It's just there, and it's just going to fall down. It's going to go in these directions, right? But in this case, the object's going around in a circle, so things are going to go on differently in that situation. So that's why, in this case, normal force is equal to mg over cosine theta. All right? So that's basically all you guys need to know. So now for these two problems. So this question here is basically a direct application of the formula for ideal angle on a road. So you guys need a recap of that. The angle theta such that no friction is needed is 10 to the negative 1 of v squared over rg. So basically the centripetal acceleration over gravity. Okay, since we're running low on time, I'm going to explain the first one now. So all we need to do is apply the formula here for the angle, which is negative 10 of v squared over rg. What is this? Negative 10 of, what's the velocity? Well, velocity, a lot of the mistakes I've been seeing is people just plug in 90 here. But if we see 90 is in kilometers per hour. So to get to meters per second, the trick I like to use is to divide by 3.6, which would mean the speed is 25 meters a second. It's actually 25 squared over 75 times 9.8. Solving this, 25 squared over 75 over 9.8. Take the negative tangent of that. It's going to give us 40.38 degrees. And this is already a pretty steep incline, looks something like this. And obviously this is not a realistic situation because in the real world, friction will be able to help out in providing centripetal acceleration. Okay, now for this one, on a flat road, the car moves at 95 kilometers an hour around a curve of radius 85 meters. What's the minimum coefficient of static friction needed to prevent skidding? Well, as we know, static friction has a maximum value, right? If if static friction is not enough to supply the centripetal force, then the car will skid off the track. So in this case, mg mu s will be in charge of centripetal force. So that equals mv squared over r equals mg mu s. Canceling these, mu s equals v squared over rg. Oh, would you look at that? That's basically what's in here. I think that's mostly a coincidence, though. So what is that? Let's first turn 95 into meters per second by dividing by 3.6. Square that, and divide by 85, divide by 9.8. Mu s is equal to 0.84. Yep. Okay, are there any questions? So now I do have some extra problems left, which involve an incline with friction on it, but I don't think we're gonna have the time to go through these. So so I think I'll just end class here. So I think you guys can leave now, and I'll see you next time. And I think I'll actually go over the last two problems on the slides by myself. And so you guys can leave now, and you can watch the solutions for that on YouTube later. All right. So I'll see you guys later. Thanks for coming. Bye. So again, once y'all guys all leave, I'll go ahead and explain the last two problems on the slide. So you guys can leave now. You can see the solutions if you want later on YouTube. So you guys can leave now. So now I'm going to talk through the last two problems here on the slideshow. So let's get started with these. So for this one, curve of radius 88 meters is banked perfectly such that a car traveling at 75 kilometers an hour does not need friction to drive around it. What must be the minimum coefficient of static friction for a car not to skid while traveling at 95 kilometers an hour? Let's first look at this. A curve with radius 88 meters is banked perfectly. So using these two pieces of information, we can use the angle theta for ideal angle to solve for what that angle theta is. So that would be b squared over rg. So what is that? That's the negative tangent of, let's first turn 75 into units of meters per second. So divide by 3.6, square that over 88 over 9.8. Take the negative tangent of all that. The angle theta is 26.7 degrees. Okay, so now we know what the angle theta is. 26.7. Okay, so now a car is going on the same ramp, same banked road, but now it's going at a higher speed. So that means the normal force in this case is not enough to supply centripetal acceleration. So now it's not going at a higher speed, which means more force is required. So that means in this case, friction is going to help the normal force. Okay, so if we divide these into components here, f cosine theta is in this direction, plus the normal force times sine theta. And this direction we have normal force cosine theta. Downward we have mg, and downward also we have f sine theta. So using all of these attributes, let's first make some room here. Using all these attributes, both friction and normal force are going to contribute to centripetal acceleration. So f cosine theta plus n sine theta equals mv squared over r. And now if we look at stuff on the vertical plane, it's just going to be, if we see here, n cosine theta is going to counteract mg and f sine theta. So n cosine theta in this case we establish a positive and a negative, minus f sine theta minus mg equals 0. Now if we move mg to the other side, we'll have n cosine theta minus f sine theta equals mg. So now we have m as an unknown and f. So how do we solve the system? Well, if we look at f here, friction is just normal force times the coefficient of friction, right? So we can write this as n mu. We're going to replace all the friction with n mu. Okay? So now if we factor out an n from the first one, we'll have mu cosine theta plus sine theta as equal to mv squared over r times normal force. If we're to do the same for the bottom, we're going to have cosine theta minus mu sine theta equal to mg over normal force. All right. So now we have these two equations here. So what we can do now is we can set these both as equal to, so let's first take v squared over r, turn that into some kind of number, right? We have a v, 95, divide that by 3.6, square that over r, which is 88, 7.91. Now for g on this side, m times 9.8. As you can see here, this equation has been multiplied by some factor to get to this one, right? By a factor of 9.8 over 7.91. So that means cosine theta minus mu sine theta, so this one times 9.8 over 7.91 equals cosine theta minus mu sine theta. So this actually equals this multiplied by mu cosine theta plus sine theta equals cosine theta minus mu sine theta. So I know this is kind of weird how we're solving systems of equations in this way, but as long as you understand how the approach to this problem works, I think you should be fine. So the rest of this is basically solving this system of equations. So now we just have theta and mu. We know what theta is, so we can just solve for mu in this case. So let's break down everything. So 9.8 over 7.91 multiplied by cosine theta. So we're looking at this term here. Multiplied by cosine of 26.7. 1.107. Wait, let me first change my pen. Mu plus what is sine theta? Sine of 26.7. 4.45 equals what's cosine theta? Cosine of 26.7. 0.89 minus what's sine theta? Well, sine theta is 0.45. Mu times 0.45. If we move all mu's to the other side, then we're going to have 1.0107 plus 0.45. So 1.557 mu equals 0.89 minus 0.45. Again, minus 0.44. Dividing through by 1.557 gives mu as equal to 0.44 over 1.557, 0.28. All right. So as long as you understood the approach to this problem, and then you would apply the abilities to solve systems of equations, then you would be able to find what mu is. Okay, so the key idea here was understanding how friction and normal force work together in this case to supply centripetal force, and then analyzing the forces on the vertical plane as well. Okay, so that's basically it. Thank you guys for listening, and I'll see you next time.